Okay, so after everything has been prepared, we need to actually propagate the electron dynamics forward in time. So the practical details will be covered by Aaron in next talk after me, and I will give an overview of the actual MATLAB script that does it, and give overview of a couple of equations that are being encoded in this script. So the code reads input data, input files as described by Yun. So list of energies and occupations in energy pop, the distributions, charge distributions for each orbital in band out, the most important part, the non-adiabatic couplings squared, the rates of the transfer between orbitals stored in the file RRR, and for master equation is the optical data, which are not needed at this step. I will not cover the luminescence. So since we are not trying to sell this code, it has never been polished to like click the button, everything will happen. So one needs to change a couple of numbers, not in the input data, but right in the body of the code, which is a not elegant style of programming, but maybe next generation of group members, if any, will fix it. So most important thing that all of us will modify as we deal with the code is this IH and IE, which stands for encoding of initial excitation. Just not want to speak too long. If you are exposed to TDDFT, right? You are. You know that actual excited state is the superposition of multiple electron hole pairs. They're correlated, there is an electron hole attraction, therefore energy of excitation is different than like HOMO-LUMO gap. But if the system is big, TDDFT is not possible. So here we are under approximation that excited state is just elementary HOMO-LUMO pair, not HOMO-LUMO. One occupied orbital and one unoccupied. There is no difficulty to expand further. Right now we are just doing elementary things. So in order to specify initial excitation, we tell how many orbitals below the HOMO where we take the electron, and how many electrons above the LUMO where we place the electron. Electron hole excitation. Then, and here, same as in the thing that John was doing, the leftmost part is the line of the code. So if the code has been distributed in the email, you can glance through and find just line and identify the right place. There are a couple of dozen of versions of the code, but I was checking that these correspond 10 minutes before the meeting. So then this loading of the energy pop file, and you see that energy pop has 3 columns. So the first column goes into this file, second column is energies goes to this file, and the last column is occupations go to this file. So again, we are going to follow the dynamics of electron that has been excited to the orbital IE, index of electron, and hole that been excited to IH, index of hole. So here we just load this red field indices, and here are some comments on the units in case you want to quote specific element of this 100 by 100 matrix for one of your debates with reviewer. And then you need to specify manually. It's possible to do by programming that code is parsing, but it's a little safer to do it manually. You specify where is highest occupied, where the orbital where your red field starts, and orbital where your red field ends. Why? Why cannot we cover each to each orbital. Because if we do not do X-ray or UV spectroscopy, we will excite very few orbitals, or few tens or few hundreds orbitals near Homo Luma. If the system is big, we never will touch something that below 1,000 or above 3,000. So we need maybe 100 or 200 orbitals in the vicinity of the gap. And it saves tremendous amount of numerical effort. So the RRR file, even if the system does have 10,000 of orbitals, we can make RRR matrix 100 by 100 by having 50 above and 50 below. And this example is made for Aaron's system with so many orbitals. It is and it is in spin orbit stuff. So another approximation that we do neglect attraction of electron and hole. In eyes of some theorists, it is a big sin. But we are doing it because we want to cover truly large systems. There are approaches that can be immediately inserted into the code that will fix this problem, but then it will be too large to start with. So right now, the RRR file includes rates of thermally activated transitions between each to each orbitals, including both occupied and unoccupied. So there are 4 quadrants. If here we have rows and columns from 0, it is not actually 0, it is from 50 below Homo. The middle is about Homo, and 100 is about 50 above Homo. So the lower quadrant here in blue corresponds to holes, and inside the quadrant it's rates of transitions from hole to hole. The upper quadrant here, the yellow, it is a rates of transition from unoccupied to unoccupied for electrons. And those off-diagonal quadrants would correspond to non-radiative transitions from occupied to unoccupied. It's a probability that an electron from occupied orbital will jump up to unoccupied because of thermal motion of nuclei. See, it is 0, or very close to 0. And in the middle, there are probabilities that such transition will happen on the Homo Luma, which will correspond to non-radiative recombination. It is small but non-zero, and sometimes we quote it. John did quote it in his paper on lifetime of excitations in perovskite quantum dots. And we all can do it. It's just picking one number from this matrix, and it's already a very valuable thing right in the middle. But we propagate electrons separately from holes. And you see here are zeros, so we can cancel these 2 quadrants and play only for rates for holes and rates for electrons. So if we look from the middle, from the upper quadrant, which is encoded in this long line, then we will look only on this part of the RRR file, focusing only on electrons. One thing. Another. Right now, RRR file has equal probabilities for going up and down in energy, like from Homo to Homo, from Luma to Luma plus 1, and from Luma plus 1 to Luma will be the same rate. But by the principle of, Fatima, did you took statistical mechanics? So when you have different probabilities going up and down, how do you call it? Detailed balance, right? By principle of detailed balance, this probability is different. it should match the Boltzmann distribution. And here we do another approximation. We can't do exact following of the detailed balance and make the transitions up and down higher or lower depending on the temperature. Here we make another strong approximation. We just cancel the rates of transition that do lead to increase of energy. So we keep only those transitions that decrease the total energy. Therefore, we parse this quadrant. So this is only for electrons. You see, it's 50 by 50, and 1/2 of this quadrant is multiplied by 0. So this is encoded in these lines, and it is approximate way to match detailed balance. Those who will work further on the code would need to make it temperature dependent and allow transitions up in energy. And even there are some parts of the code that do it, you just cancel it to make it simple and clear. So right now, we are looking only on electrons. For the holes will be the same story. So electrons, one particle, one electron that has been promoted to the originally empty orbitals. And for each orbital in the conduction band, from each to each, we have this former RRR file, which is now called RE, like red field for electrons. Questions? Okay. So a little technical details. I'm not blocking. So here is the problem that John was facing and resolving. If your couplings have been computed at different temperatures, if your system does have subgaps, if the energy offset between orbitals is large enough, the rate of transitions can be very, very small. So it can range by several orders of magnitude. Aaron also, we all were facing it, or we will face it. Aaron did have the 3 orders of magnitude difference because the transfer was through bond or through space. And you did see this effect by having materials with very large gap. So we need to be able to cover like from femtoseconds to seconds, or at least to microseconds, or right? So if we will have it, we need to propagate forward in time. But if you will make time step smaller than femtosecond, it's good, but it is too expensive. If you have time step larger than femtosecond, we can, but if you take like 1, 2, 3, and if you go to nanosecond, to picosecond, it will be 1,000 steps. If you want to go to nanosecond, it will be how many? Million steps. If you want to go to whatever is next, milliseconds or microseconds? Microseconds. Then we need to do billion steps, which can throw the head of our computer. Therefore, we are doing non-equal time step. Each step has different lengths. And later you will see that it is allowed here. So the time step expands exponentially. So through this equation, we have a grid which is spaced equally, about 500 time steps, but offset between actual value of time spaces non-evenly. When we look on a short time, they're spaced very finely, close to each other. When we are looking to longer distances, the offset increases. So it is encoded in here. The variable S will be needed later when we will do green figures for energy distribution, and therefore it has the size of the grid, which is spans all energies where orbitals of our interest are inserted with fine enough step. Okay, so remember our discussion with Dane. First programming step, second programming step, third. Occupation of orbitals, distribution in energy, distribution in space. Energy and space are just visual, but occupation of orbitals is main thing that this code is doing. So in few slides, right now I'm showing it a little too early, but otherwise we will be bored. So it is the goal that we will reach in 3 slides. So it is occupation of each orbital in the conduction band if the no, it doesn't allow annotation right now. If originally we put 100% occupation to LUMO plus 10, right? So as time passes by, it will lose occupation, and some orbitals, LUMO plus 9, plus 8, plus 7, will gain a little occupation. The LUMO itself was empty, and as time passes by, it will gain all population. So it will be cascade thermalization that we are modeling. These time steps, right now they are discrete, but in fact, between they are non-equally spaced. At the very beginning, the spacing is about femtosecond. At the very end, the spacing is more than a picosecond. It's just increasing step. So the trick, numerical trick to do this code was borrowed from very elementary approach to basic quantum mechanics, where main principle that one takes Hamiltonian, diagonalizes, gets eigenvectors, and use them, and each of them evolves in time with right frequency. This idea of the quantum mechanics, where one diagonalizes Hamiltonian, can be extrapolated to a very different type of operators and very different type of eigenvectors. So right now we will use the same coding style, but we will think about completely different things. So we will diagonalize not Hamiltonian, but operator of Liouville plus Redfield. So Liouvillean operator diagonalization, Redfield operator diagonalization. Eigenvectors will be not the eigenstate of Hamiltonian. It will be something that is hard to imagine. So right now it's mathematical abstraction. So, but the core calculation was borrowed from there, and some notations a little non-ideal. So psi here it is the same name as one would use for wave function, but it is not wave function. So it is initial state for occupation of electron orbitals. I'm not showing it here, but this time step number 1, here all range of orbitals, and it was set up that all of them are equal to 0 except the one that corresponds to index of electron, IE. So we do set it up. Now we set up the size of our space. It is last orbital included in the RRR minus HOMA, so only upper quadrant. And the matrix RE is our quadrant that corresponds whatever comes from Redfield related only to electrons. So if you would do this coding in C++ or in Fortran, this line would expand in 20 lines or maybe 200 lines, or just calling some linear algebra packages with subroutines. But in MATLAB, it is just one line of diagonalizing matrix Re and funneling the results of diagonalization in two objects. So eigenvalues coming into the second one, into the D, and eigenvectors are stored in matrix form, 1, 2nd, 3rd, and stored in this matrix U. So this is numerical solution of eigenvalue problem. I have a big temptation to say that the rest is trivial. So, Liouvillean plus Redfield act on density matrix eigenvector. Density matrix eigenvector gives this eigenfrequency and again eigenvector. After we get these eigenvalues and eigenvectors, we need to match initial conditions. So this solution will be universal for any initial conditions. In fact, we have potential to know everything after we do this diagonalization, but it doesn't help us, this knowledge. We need to get something that we can observe for specific initial excitation. So we need to match initial condition. Therefore, this is another excellent thing in MATLAB. It is solution of system of linear differential equations, like this 100 equations in one line. So we find expansion coefficients. We find this vector C will tell projection of the initial state onto each of eigenvectors. So this vector C, which will have the same size as many orbitals in conduction band, will tell how much given eigenvector contributes to this initial condition. And we solve for this initial condition at time 0. Again, how much given eigenvector contributes to given initial condition. Now we construct time propagation. So we take the eigenvector of density matrix of Liouville-Redfield operator that we found through diagonalization. It evolves in time as exponential to the power of this eigen frequency times time. And right now it is not things that in quantum mechanics, but it is standard thing in linear differential equation, right? And here this, it's not the best notation, I just didn't found something better. It is the thing that we stored in the vector C, initial conditions, projections of the density matrix at initial time, at time 0, onto each of eigenvectors. So each eigenvector contributes to solution with such proportion which depends on initial condition, right? And then we make summation, this letter, strange letter xi just runs over all eigenvectors.
So it's a ket or a Bra and a ket?
Let's not do Bra and ket because it is Liouville in space. We will make it. It's not the best notation.
So this one is just the C inverse?
Yes. From one angular bracket to another one, it is a letter C. So this row for indices I and j bigger than HOMO are found in these lines. So this vec is parsing the expansion coefficient number k out, so it is a mask that by it will be 1 at the place corresponding k and zeros before and after. So if you multiply this mask by vector c, then we will get contribution only for one value of this index. So we add together all summation that we did before plus expansion coefficient. Sorry, this vector is used to parse eigenvector. This is by index. So by multiplying matrix of all eigenvectors by this vec object, we will get only one eigenvector. And then the time evolution is gotten by frequency number k times t. Okay, and then we add all of them together and get the dynamics of only diagonal elements of density matrix for the electrons. If we expand this code further, and we need to include off-diagonal elements as well, but there is a theorem that in several cases one can propagate them separately. And I do have versions of the code with off-diagonals, but again, it's all grows to a size that we cannot review in one meeting. Any questions to here? So it matches your favorite subject of linear differential equations that you recently took.
I didn't like any of them.
Huh?
I didn't like any of that class.
Okay. And this line is not needed. If everything is encoded correctly, change nothing. I just did it as a safety emergency just in case. If you do numerical propagation, sometimes the norm is not conserved, and this is just normalizes this occupation so that their summation always is equal to 1. But it's just a numerical measure. Adds nothing to the algorithm. And here we are funneling. So this psi, actually it is the diagonal part of density matrix for electrons as function of time. But the name psi is not ideal for such object, so we put it into PPE. I didn't find better name because I do not know the letter rho on the keyboard. P just because my hand was shaking, and E for electron. For holes it will be PPH. So I'm skipping the things for PPH, otherwise we will be out of time. So then remember, occupation of electrons, distribution in energy, distribution in space. We are done with occupation of orbitals. It was in this place before. Now we are looking onto distribution in energy. So again, I'm showing the outcome before, otherwise it will be too boring to follow. So this is the main outcome of the code. If you learn how to generate it, you can do competitive publications. You need to invest time into being able to generate them for different initial conditions, for atomistically computed couplings. So what does it mean? This corresponds to excitation at time 0. We take an electron from occupied orbital and promote it to unoccupied. So the blue corresponds to absence of electron, yellow corresponds to presence of electron, and green means that distribution is the same as for ground state. And as time passes by, the electron dissipates its energy into thermal vibrations. So its energy drops from LUMO plus 10 to LUMO. Hole also dissipates energy into thermal vibration, and therefore it floats up to the maximum of the valence band. So after some time they end up on the HOMO and LUMO, on the edges of the bands. Okay? So how do we program it? We take the occupation of each orbital at each time and multiply it by distribution function that is centered at the energy of given orbital. Right? And under this delta, we understand not true delta function, but something with finite width. So, and then we subtract the equilibrium distribution for green. Slice. So it is distribution at time t is PPE, which is element of density matrix of orbital I at time t, times exponential of Gaussian, with Gaussian representing this delta function at energy of electron orbital number I, right? Since those are continuous functions, then instead of sharp peak only in the exactly energy of orbitals, we get kind of smearing. And this is especially important if you have very high density, or if the energies of orbitals change in time. And then the slice for each time step is accumulated into matrix that is growing bigger and bigger at each time step, and then it accumulates so that on one dimension it will be energy, about 500 steps for different values of energy, and on another axis it will be time steps. So this S, at this point, it will be upper part of this image. Make sense? Okay. Yeah, we can plot it. Here you see since time steps are non-equal, we can either request logarithmic plot or we can do linear plot, but on the x-axis show log of time, so that we cover from picosecond to the -3, which is femtosecond, 10 femtoseconds, 100 femtoseconds, 1 picosecond, 10 picosecond, 100 picoseconds, 1 nanosecond. So here we are plotting, maybe I just by error deleted the slide, but these lines, dashed and non-dashed, corresponds to average energy of electron and average energy of hole. Let's see. Yes. So we take energy of orbital times occupation of orbital and run over all orbitals. And then this is weighting. Weighting, not like I'm waiting for the bus. Weighting like giving weight to probability. It's probability that this energy was found, right? And then if sum of all probabilities is 1, then after the summation, it will be expectation value of energy. So this dashed line is this expectation value of energy as function of time, which is PPE times energy, which is stored in a vector. We are very close to beginning of Aaron's presentation and end of May. So another approximation, if we assume that this function is a linear decrease, then we can extract approximate time when it experience this transfer from excited to non-excited. So something a little bit shorter, or of the order of 1 picosecond, by this expression. If you hate this expression or do not like it, you can just numerically take this line, feed it into Excel, and make fitting to single exponential or something else, or to the origin, but I'm doing it very simple way, almost manually, simple programming. So this equation corresponds to fitting to a single exponential decay. And then for electron, it gets the rate of 2 point something inverse picoseconds. If the rate is 2 inverse picoseconds, or 2 picoseconds minus first, it means that time of transfer will be 1 divided by this number, which will be half of a picosecond, right? Make sense? So it's 1 picosecond, and it experiences this transition somewhere before 0. So it agrees with this figure, but it gives more algorithmic way how these numbers were obtained. The whole relaxes later, therefore the rate is lower, right? So these two numbers can pop up in the command line of MATLAB after each run of the code. One of the standard tasks that we do, compute everything, as Yulun has explained and everyone before me, and then play with the two very first lines that I declared at the first 10 seconds of my presentation. Index electron, IE, and index of hole, IH. Change initial excitation and see how the rates respond to the change of initial excitation. This is a very simple thing to do practically, but it is something valuable and unique that standard codes do not have, and that we can attract attention of experimentalists who are doing time-resolved experiments like femtosecond spectroscopy or whatever. Response of the relaxation rates to initial excitation.
How does the code know that the first relaxation isn't the one that it should report out?
Right now, this version of the code assumes that everything goes as a single exponential, which is here it is a lie. It is one exponential then second. I'm not telling that this one is the best, and you are exploring this opportunity and splitting the time range of on two intervals.
Mm-hmm.
But these things can be included if you make it a commercial code for sale, like a Gaussian for 10,000 license, or we can do individually in our research projects. But if you want to have something simple that we can explain in 20 minutes or whatever, a couple of hours, then let's start with simple things. It's not ideal. It is a very strong approximation. Another parameter is what we take as an infinity in this equation. Well, infinity is the last point of simulation, whatever, nanosecond or how much time we have we span over. There is a unit of code to do the third thing, the distribution of charge in space for charge transfer, and there is a fourth thing that is in the descendant code for photoluminescence. No time right now. This could be the last slide. Yes. Any questions? Any questions? 1? Any questions? 2? Any questions? 3. Okay, I'm free. And the next presentation is by Aaron, who will teach us more on practical aspects of running this code. Right now this camera is tuned to there, but if you do not like walking there, I can focus it on you. And oh, here, let me distribute.
Yeah, so as Dmitry mentioned, this is more just a primer on the practical things you have to know on how to actually just run the software based on the things you want to simulate. So when you open the code, the first thing you're going to see is this top line here, for I, H, and IE. And those basically just change your initial conditions for the optical transitions you want to look at. So in principle, you can choose any numbers that you put in there. The code would probably run it. But you want to choose good ones so reviewers don't ask you, like, why are you looking at these transitions? So normally we want these to correspond to your oscillator strengths, which you compute earlier. So you would already know those values. You would just have to look them up in the cluster before you run the simulation. And so on the right-hand side, it kind of shows you what each of these parameters respond to. So for IH equals 1, that would correspond to your HOMO. And then IE equals 1 would be your LUMO. So yeah, it's just good to